Hello, ladies and gentlemen. Welcome back to Chemistry Notes. We're going to be looking at chemical equilibrium today. These go along with the PowerPoint that I posted in Google Classroom for you, but I'm also going to walk you through them, especially because of the calculations. I want to make sure you understand how we set those up. Today, we're going to be focusing on equilibrium and equilibrium constant expressions. So starting off, how does equilibrium work in a chemical reaction? It works with something called a reversible reaction. With a reversible reaction, the reaction can go in both directions. It can go in a forward direction and in a reverse direction. So a reversible reaction is one in which the conversion of reactants to products and the conversion of products to reactants can occur at the same time. And we know we have a reversible reaction because of this double-sided arrow. The double-sided arrow shows us that the reaction can go in both directions. Now, in this reaction here, we see nitrogen reacting with hydrogen gas to produce ammonia. Or if we look at it in the opposite direction, we see ammonia decomposing to produce hydrogen gas and nitrogen gas. In the forward forgot the R there. In the forward reaction, hydrogen and nitrogen combine to form the product ammonia. The forward reaction is the traditional way of looking at a reaction. In the reverse reaction, and I'm shortening reaction with RXN there, that's just kind of a symbol for reaction. So in the reverse reaction, ammonia decomposes into the products of nitrogen and hydrogen. As a reaction proceeds, the rate of our forward reaction continues to decrease, and the rate of the reverse reaction continues to increase until the two rates are equal and their concentrations become constant. Which is what we see here in the graph. So in the very beginning of the reaction, we start with no product. We have zero ammonia there. And we start with our reactants, nitrogen and hydrogen. Now, as time goes, you start to use up the nitrogen and hydrogen. They are reacting to produce ammonia. So ammonia's concentration is increasing. Nitrogen and hydrogen's concentration are decreasing. Eventually, when the forward rate and the reverse rate start to equal, then the concentrations of all three of the substances become constant. You can see here that their concentrations are not equal, but they are constant. They plateau or level off at the same rate over time. That's how you know something is at equilibrium. So equilibrium occurs when the forward and reverse rates of a reversible reaction are equal. This is really your definition of equilibrium there. So this is represented with that double-sided arrow in the reaction. We saw that. You could either have it look like this, or sometimes you'll see a double-sided arrow look like that as well. The concentration of the reactants and the products are constant. We mentioned that in the graph above. You can tell that they are constant because they have constant color or constant pressure. That's just an example of how you can tell they're constant. Constant concentration does not mean equal concentration. So up here, we see that they are not equal. If they were, they would all converge into one line. They have three separate lines that just plateau or show that they have constant concentration over time. Now, in order for equilibrium to occur, three conditions must exist. You must have a closed container. If the container is not closed, you're going to allow product to escape. And if that product's escaping, it's never going to be able to go in a reverse order and produce a reactant again. You need to have constant temperature and pressure. When you manipulate temperature and pressure, you're going to manipulate the equilibrium reaction. And you also have to have a reversible reaction. For example, burning paper will never be an equilibrium reaction because that reaction is not reversible. You cannot turn the burnt ash back into real paper. It just doesn't work that way. So it has to be a reversible reaction as well. A big part of what we're going to be looking at with this section, with this chapter, is writing equilibrium constant expressions. Equilibrium constant expressions shows the ratio of products to reactants found to the power of their coefficients. So that's what the exponents become there. So for this generic reaction here, this is what our equilibrium constant expression would look like. An equilibrium constant expression is a KEQ. So you're going to hear me say the term KEQ often. Here you can see that the concentration of C to its coefficient is the C power. Concentration of D to its coefficient of D. Concentration of A to its A power, and the concentration of B to its little b power there. Where those brackets there stand for molar concentration. And C and D were our products, and A and B, of course, are the reactants. So our equilibrium constant, or KEQ, is expressed as a ratio of products to reactants concentration in an equilibrium. This is really, so KEQ is equal to the concentration of products over the concentration of reactants. So the brackets stand for molar concentration. The coefficients in the balanced equation become exponents. And since solids and liquids, they have constant concentrations. If you have a solid, molar concentration is how many moles you have per liters of solution. Well, if you have a solid, it's never even in liters of solution. So it doesn't really necessarily have a concentration. So we say that it has a constant concentration. Liquid is the same thing. If you have a liquid, that means that it is not dissolved in water. It's just that pure liquid, and it has a constant concentration. So they are not included in writing our KEQ expressions. Only substances with variable concentrations are. So those will include aqueous substances and gaseous substances. So only aqueous and gaseous substances are included in your KEQ expressions. All right, so our problems that we're going to practice here is writing the KEQ expression, our equilibrium constant expression, for different reactions here. So here we're looking at the decomposition of baking soda. When we're looking at this, the very first thing you want to address is the states of matter. We said gases and aqueous substances are included in equilibrium constant expressions. Solids and liquids are not. So the solids, right away, I'm marking those off. Those are not included in our equilibrium expressions. When we write these, it's going to be a ratio of products over reactants. So we have carbon dioxide to the first power. You can either write the 1 or you don't have to write the 1 because 1s are understood. And that's going to be multiplied. We're multiplying these things. That's going to be multiplied by the concentration of water. Since water is a gas here, we have to include it in our KEQ expression. That is also to the first power. Since our reactant is a solid, we don't have to include that. We really don't need to write anything on the bottom. You can write it over 1 if you want to, but again, you don't really need to. All right, looking at some more practice, we're starting with problem A here. These 3 substances are gases, so they will all be included in our equilibrium expression. We start by writing our product, which is sulfur trioxide. And that is to the second power. Since it has a coefficient of 2, we're going to write that to the second power. Divided by our reactants. So we have sulfur dioxide there, and that is to the second power because it has a coefficient of 2. And oxygen gas, and that is to the power of 1 because it has a coefficient of 1. For letter B here, again, we start by looking at states of matter. A is a solid, so we're not going to include that in our equilibrium expression. And AB3 is a liquid, so we are also not going to include that in our equilibrium expression. So it's the products over reactants. Well, my product was a liquid. We're not including it. So I'm going to write a 1 there. That's going to be over our reactant of B2, and that is to the third power because it had a coefficient of 3 there. For our last problem here, letter C, you can see all of the substances are gases, which means they will all be included in our equilibrium constant expression. We're going to start with our products. It's always products over reactants. So we have carbon monoxide, and that is to the first power. Again, you don't have to write that because ones are understood. And remember, these are multiplied by each other. So that's going to be times concentration of hydrogen. Its coefficient is 3, so I'm going to bring it to the third power. You're going to divide that by the concentration of methane to the first power. Again, you don't have to write the 1. These are multiplied, so you want to either write the multiplier sign or don't write it, but sometimes kids try to add these, so it's important that you know that they're multiplied. That's going to be times the concentration of water, and that will be to the first